the PIN diode or pin diode. In this lecture, the construction, properties and applications of the pin diode will be discussed. The construction of the pin diode can easily be understood from its name itself. The pin diode, where this P stands for P-type region or P-type semiconductor, I stands for intrinsic semiconductor, and N stands for N-type semiconductor. Now you can see the construction over here. The first layer is a P layer, and next another one is a P substrate, then this intrinsic layer, next one is the N substrate, and then N plus layer. So this P region followed by this intrinsic region and followed by this N region makes this name, that is the PIN. Generally, a pin diode can be constructed in two ways, or using two methods, either by the mesa structure or by the planar structure. In the case of mesa structure, a previously doped N-type semiconductor is grown or developed over one side of the intrinsic region, whereas a previously doped P-type semiconductor is grown over the intrinsic region, that means on the other side of the intrinsic region. In the case of planar structure, a narrow, thin epitaxial layer is imposed on either side of the intrinsic region in order to realize this P plus region and the N plus region. Using this diagram, the doping concentration of a typical pin diode is shown over here, and as P is doped with a P plus region and N is basically denoted as N plus region, which means the P side and N side are highly doped, whereas this intrinsic region, this is the longer region, is undoped region. So therefore the concentration is higher on the P side as well as on the N side. The major advantage of this PIN diode is that the resistivity is within the range of 10 to 10 kilo ohm per centimeter, and the most important part of the pin diode is that its resistance, which is associated with this intrinsic region, is variable with the bias current, and this resistance of the intrinsic region can be expressed as this one. Here this intrinsic resistance, or that means the resistance associated with this intrinsic region, depends on this current I naught, which is shown over here as I naught, and this I naught is the bias current. From this expression, it is also clear that as bias current increases, the resistance within the intrinsic region decreases, and when the bias current decreases, the resistance gets increased. Now let's understand a few properties of the pin diode which are associated with the wider intrinsic region of the diode. Since the intrinsic region means it's undoped, the entire depletion region during the application of the reverse bias appears across the intrinsic region, and that causes the high breakdown voltage of the diode. But the wider intrinsic region also causes the low transition frequency, because the carrier needs longer time to transit from one junction to the other junction. In addition to that, already we have seen that the wider intrinsic region increases the resistance of that, and in addition to that, the resistance is a variable one. Another advantage of the wider intrinsic region is that the area covered by the intrinsic region is obviously a larger one, and that increases the power handling capacity, and also it produces large diode junction capacitance. Although the junction capacitance is very large, but the variation of the capacitance is negligible one because of the highly resistive intrinsic region. The high resistivity also causes the low RF loss, because you know from the basic theory of electromagnetism that when an electromagnetic wave propagates through a medium, the more the conductivity of the medium, the more loss the electromagnetic wave gets experienced. So in this case, since the resistivity is higher for a pin diode, the loss of the RF wave is smaller. And this point I already have discussed at the beginning of this slide. As you know that the internal capacitances such as these junction capacitance are responsible for the bandwidth as well as the cutoff frequencies of the device. So in this case, since the junction capacitance is larger one, the bandwidth is narrow and obviously the cutoff frequency is much more smaller. Although pin diodes with higher cutoff frequency and wider bandwidth are also available in the market. Here, an equivalent circuit of the pin diode is presented, and on the right side, the equivalent circuit in the case of forward bias and in the case of reverse bias are also presented. Now, let's understand the equivalent circuit for the pin diode in general. LS, this is the lead inductance, and it appears between the external connector and with the internal semiconductor device. And after that, there exists a series resistance followed by the junction capacitance, junction resistance, and the diffusion capacitance. CP stands for the parasitic capacitance, which is associated with the packaging of the pin diode. The CF is introduced due to the fringing effect of the pin diode, and that is why this capacitor is called the fringing capacitor. And this one is the most important two part, that is the capacitor associated with the intrinsic region, and this one is the variable resistor associated with the intrinsic region. So that is why the variable symbol is placed over here, and this resistor is only for the intrinsic region. Now, in the case of forward bias, this resistor's junction resistor, it is very smaller, but as already I told that the junction capacitance are very large for a pin diode, and the diffusion capacitance, which also appears large for a pin diode. Therefore, in the case of forward bias, these three components can be replaced as a short circuit. So therefore, after this RS, if you place a short circuit, then these two components should appear directly after this RS, and that is why the equivalent circuit in case of forward bias is approximated as shown over here. On the other hand, in the case of reverse bias, that Ri becomes very large. Already I have mentioned that it is around 10 kilo ohm per centimeter. So therefore, for this large impedance in reverse bias for the intrinsic region, you can approximate it as an open circuit. So that is why that resistance is not included in this diagram over here, and all other parameters remain same. So that is why the equivalent circuit in reverse bias is represented in this way. Pin diode is a very useful device and which of plenty of applications in microwave frequencies. In addition to that, it also has applications for optical frequencies also. But here, as per the demand of this particular subject, I am going to discuss a few applications associated with the microwave frequencies. So first one is that microwave switch. As you know that the resistance of a pin diode increases with the bias current. So there is a DC bias is applied to the pin diode over here, and the RF signal is applied at this terminal of the network. So this is the input terminal of the network, and this is the output terminal of the network. Now, when the RF signal exists at the input terminal of the network, and you have applied the DC bias in such a way that you put this pin diode in forward bias, then a low resistance path will be available from this terminal to this terminal. So therefore, the RF signal will not be available at the output because the entire RF signal will be bypassed through this diode. On the other hand, during the operation, if you make the bias so that the pin diode is in reverse bias, therefore the entire RF signal will be available at the output port. So in this way, you can switch or you can on or off the availability of the RF signal at the output port. Such kind of switch is called the shunt mount, and in addition to the shunt mount, there exists a series mount also. In the case of series mount, the operation is just reversed to that of the shunt mount. That means when we apply the DC bias in order to make this pin diode forward bias, then the RF signal will be available at the output, which is just opposite case of the previous one. And when you will put the pin diode in reverse bias, then obviously the RF signal at the input terminal will not be available as the output. But as we know that nothing is ideal, so during the switch off mode, a smaller amplitude of the input RF signal will be available as the output, and it is applicable for both the cases or both type of mount. Next is the phase shifter. So here two type of phase shifters are demonstrated. The first one is the transmission type switched line phase shifter, and the second one is the transmission type loaded line phase shifter. In the case of switched line phase shifter, you can see when these diode D1 and D2 will be in forward bias, then this signal, this RF signal will take this path, and a phase corresponding to this path length I0 will be produced, and that is equivalent to phi naught is equals to beta times L0, where beta is the propagation constant of the RF signal. On the other hand, if this diode D3 and D4 is forward bias, while this diode D1 and D2 in reverse bias, then that signal will find this path where the path length is L1, and the phase corresponding to the L1 path can be written as beta times L1. Such kind of phase shifting operation is available only for microwave frequencies. It is not applicable for the low frequencies because, as already you know and I have discussed in my earlier lecture, that in the case of low frequency, these circuits or the wavelength of the low frequency signals are much longer than the dimension of the circuits. Therefore, the low frequency signal in the case of forward and reverse bias diode, if you even consider it is a ordinary diode, although it is not, but if you consider they are ordinary diode, and when you are applying this mechanism, so this phase shifting operation you are not going to be experienced, because in the case of low frequency the wavelength is much larger than the dimension of the circuit. So therefore that phase shifting operation is not possible to be observed. But in the case of microwave frequencies, as we know, the dimensions of the devices becomes comparable with the microwave wavelength. Therefore, when the microwave signal traverses a path either from this direction or from this direction, the path length becomes equivalent to some phase associated with the product of the phase constant times the path length. So in this way, by changing the biasing of this pin diode or this 4 pin diode in this case, you can introduce a phase difference such as these delta phi you can write as phi naught minus phi 1. So this is the phase difference you can introduce over here, and this is applicable for the transmission type switched line phase shifter. In the case of loaded line phase shifter, these two diodes are placed at positions which are lambda by 4 distance, or the quarter wave distance apart from each other. The idea is that, as you know from the theory of the transmission line, that as you move half wavelength distance from the load terminal, everything remains same or repeats itself. On the other hand, if you move a quarter wavelength distance from the load terminal, then everything alters. That means the property of the load impedance as well as the input impedance alters. So that is why that idea is utilized over here. You can see the two diodes are placed which are the lambda by 4 distance apart. So thereby making these two diodes forward bias, short circuits are realized at these two positions which are lambda by 4 distance apart, and that causes the input impedance inductive. On the other hand, if you make these two diodes reverse bias, the input impedance will be capacitive in nature. So in this way, A phase shifting operation is achieved in the case of loaded line phase shift. Amplitude modulator. This is a very simple operation. You can see from this diagram that this modulating signal, which is low frequency in nature, is connected to this bias control of the pin diode, and the carrier is applied across the device. Now, depending upon the modulating signal, the biasing conditions of the pin diode will be changed, and according to that it will modulate the carrier signal, and the amplitude modulated wave will be available across the output terminal. Next one is the attenuator. Here, as we know that by increasing the bias current we can decrease the variable resistance of the pin diode associated with the intrinsic region. The attenuation of the input RF signal can also be reduced in this way. That means by reducing the intrinsic resistance caused by the increase of bias current. On the other hand, if you want to attenuate more, then reduce the bias current and it will increase the intrinsic resistance, and it will oppose the input RF signal to be available at the output. In addition to the series mount system, a shunt mount system is also available, but here the operation is just reverse to that series mount system.